Today I'll be talking about Lagrange's remainder or Taylor's remainder, which is just whenever we have a Taylor series expansion of a function, if the expansion is not infinite, meaning we don't include an infinite amount of terms, then there will always be some sort of error between our actual function and our Taylor approximation of the function. And one way to numerically compute or estimate this error is through the Lagrange's remainder, and this will be the error over here. So our function f of x will equal our Taylor expansion up to the power of n plus this remainder term, and this remainder term will be the n plus 1 derivative of f evaluated at a point epsilon over n plus 1 factorial times x minus x0 n plus 1, and this point epsilon is just a point between x and x0. So for example, over here I have the function e to the x, and here I expanded it. The dashed purple line is the Taylor series expansion up to the power of 2. So include the constant term, the first term, and the linear term, and we can see they're very close to, like, we're expanding at the point x equals 0. So this would x0 would equal 0. This is the point of our expansion, very close to it. In the interval minus 0.5 0.5, the function approximates it very well. But as we get further out, as x grows, the error gets bigger. So for example, here when x equals 1, the error would be this vertical line between the dashed line and the blue line. So one way to compute this error is through the Lagrange's remainder term, and this epsilon term, in this case, if x is 1, would be epsilon would be one value between 0 and 1. So we're expanding at the point x equals 0, we're looking at the error at x equals 1, so we'd have to take the n plus 1 derivative of f at a point somewhere between here, so maybe 0.2, 0.7, whatever. And we don't know what this point exactly is, we just know that it is a point between x and x0. So this is Lagrange's remainder, and again, why is our error remainder term even useful? Well, let's say that we want to approximate a function with its Taylor series, and we want a certain amount of accuracy. We don't want to include every single term up to infinity or like a million. Let's say we want, in the interval between 0 and 1, we want our function to approximate e to the x, and we want the approximation to be better than like 0.01 for every point between 0 and 1. So we don't want our error to be greater than 0.01. Well, we can just use this over here. We can say that this, let me just remove this. We can say that this error bound has to be less than or equal to 0.01, and then we can bound this, usually the f n plus 1 derivative at this point, epsilon, for let's say for any, we can just say for any x between x and x0. There's usually a smart way to bound such functions. Let's say this is less than or equal to m, and then we can replace this. We can replace this over here by constant m, and then we can easily solve for n. We can solve for n, and then we can find out to which expansion we need to expand. To which, to how many terms we have to include in our Taylor expansion, such that our approximation will be accurate enough. And again, if n equals 2, that means we include 3 terms. So the first one, the constant, the linear one, and the second one. So that's kind of why this is useful. And now, how do we actually get to it? Because it looks kind of weird. Like, I always thought it's kind of really hard to derive, but actually it's not really hard at all. It's not that hard to do it at all. It's actually a really cool and clean process. It works out so well. All we're gonna need is Rolle's theorem. And Rolle's theorem, if you don't know what it is, it's a really simple theorem. Just saying that if you have a function, defined, or just if you have any function and you're looking at it from an interval a to b, and the function is continuous and differentiable in that interval, and if the function, let's say here this is f of a, and then it's doing whatever, and then boom, at f of b it has the same value. So if f of a equals f of b, then we know that there exists a c. Wait, this is the wrong symbol. We know that there exists a point c somewhere between the interval a and b, such that the derivative of f at c equals 0. Which just means that we know that there exists a point between a and b, such that at that point the function will have slope 0. And this happens here and this happens here, and it kind of makes sense. Like whenever if it's a straight line, the c will be every single point. But if the function curves or whatever, like at one point, if f of a equals f of b, there has to be at least one point where the derivative of f is 0. So there exists a c between a and b. That's the only thing we're gonna need. And how is this connected to the error term? What we're gonna see. First of all, what even is our remainder term? I'm going to define our remainder term, Rn of x, as being our function, f of x, minus our Taylor approximation, Tn of x. And this is the Taylor approximation up to the, up to degree n. So if n was 2, it would be these first 3 terms. So this will be our error. Our error will just be our function. Like this example, it's e to the x evaluated at x equals 1. This is the value of our function here, like 2.69 or like approximately. And then this will be our approximation, and the error is just the difference between these two. So how do we know? We want an expression for Rn of x that doesn't include, that doesn't just include this. Like we want a better expression, one that also doesn't include the actual function f of x, because it can happen that sometimes you don't know your actual function f of x, like what it is explicitly, but you know all of its derivatives. For example, the function is defined with an integral or something. Like it's easier to know the derivatives of the function than actually knowing the function itself. So this is why we don't really want f of x in our in our equation. We just maybe want its derivatives. So how do we transform this expression to get rid of f of x? Well, I'm gonna first of all define another function, and I'm gonna call it capital F of t, and we're just gonna define a new variable t, and it's going to be the exact same function. It's going to be f of t minus t n of t, and we're just going to use this again. This is just a smart trick. T is just a normal variable like x. There's nothing special about it. It's just a different variable. Oh my god, I need to make this t better. It's just a normal variable. We just have two variables now. We have x and we have t, and we'll see when we're going to use Rolle's theorem. Like this t will disappear eventually, but it's just going to make the algebra easier in between. And now we want to say what we know about this function f of t, like capital F of t. When I say f of t, I refer to this one. So what do we actually know about this function? Well, what we know is that f of x0 equals 0. And again, here when I say x0, here I wrote it as a, but whenever you write the Taylor series, this can also be x0. I'm just using different notations, but basically that means that the function, at the point where we're actually expanding it, the error will be 0, because our function f at x0 equals x0, and our Taylor expansion at x0 also equals x0. That's how the Taylor series is defined. If we replace here, for example, if we replace f for x0, or I mean for a in this case, all of these terms will delete, and we just stay with the original term. The Taylor series is constructed in such a way that it equals the function at the point where we're expanding. And here we're expanding at a equals 0, and see our approximation at x equals 0 is exactly equal to the actual function. And we can switch a. It doesn't. We can expand the Taylor series at any point. Here I'm just expanding it at 0. But so this, we know that this will be true, but we also know that the first derivative of f at x0 will equal 0. And now why is that true? And we also know that the second derivative of f at x0 equals 0. Why can I say that? Well, again, that's how the Taylor series is constructed. I hope you know something about the Taylor series, but it's constructed in such a way that all of its derivatives up to the point n, if it's if we n is just the amount of terms we have in a Taylor series up to that power over expansion. This function is designed that all of its derivatives will equal the derivatives of our actual function at the point of expansion. So we can only say this for the point x0, or only for the point a. We can't say this for any other point. You can easily see this. If you start taking the derivatives, then only the actual derivative term will stay. I mean, I hope you know this about the Taylor series, but again, that's literally how it's constructed. The Taylor series of a function is just a series that will match every single derivative of our function at the point where we're expanding it, up to the point n, which is just the degree of our expansion. So we know that up to fn, the derivative of our function at x0 will equal 0. Now we have this crazy information, and we want to use this information, and we're going to see how we're going to use this information to get to our final answer, because this is really powerful. I mean, this is really useful. And what we're going to now do is, this is the last time we define a new function. Now we're going to define yet another function, g of t, and we're going to and this function will just be f of t, x minus x0 to the power of m plus 1 minus f of x to the power of, times t minus x0 to the power of m plus 1. And now this seems kind of random. Why did we define a function like this? Well, it's kind of hard to actually think of like why you do this exactly, but we're going to see, if we kind of know that we're going to use Rolle's theorem, we want to make a function such that well, actually, before I should just mention that t is our variable here. T is what changes, and x, we fix x and x0. So x0 is obviously a constant. It's where we're expanding our function, and x usually varies, but for this function x is just a constant, so we just choose x as any x right now for our calculations. But these are fixed, and we kind of we include f of x and f of t so that we can vary t, and this stays constant. And ideally with Rolle's theorem, we want to find some points where g of some point equals g of another point. So this is kind of why it's subtracted here. So that it's kind of, we're kind of trying to get to this scenario, and also we have the information up to the nth derivative of our function. So we include these terms here because we kind of assume that we're going to take some derivatives of g, and so that these n's will disappear. It's kind of the actual intuition behind why you define this function g of t like this is kind of hard. It's the only weird thing, but once you do, everything's easy. So you just define this function, and now we'll see that everything else will start being really clean and really satisfying. So first of all, let's look at what g of x equals. G of x equals, well, f of x, as t is the variable, times x minus x0 n plus 1. Again, these are just constants. You can just imagine this whole thing as a constant because x and x0 are fixed. And then minus f of x, this is also just a constant, times t is the variable, so x minus x0 n plus 1. Well, oh my goodness, what happened? These two terms are exactly the same. So we subtract them from each other, bang, this equals 0. Now, what about g of x0? Because, again, we fixed the 2 points x and x0. So we're focusing on these 2 points right now. What is g of x0 going to equal? Well, that's going to be f of x0 times x minus x0 to the power of n plus 1 minus the constant f of x times x0 minus x0 n plus 1. Here something else happens. First of all, we can see that x0 minus x0, bang, this term goes to 0. But this term, what happens to this term? Well, remember about the information we have. We know that f at x0 equals 0. So this over here also equals 0, multiplied by constant, bang, this will just equal 0. This is kind of the first clean thing. And now we see that g of x equals g of x0. We constructed g. This is kind of the motivation behind g. We constructed it in such a way that g of x equals g of x0 because, again, we know we have to use Rolle's theorem. So now, because, this is a function, we have our value x, we have our value x0, we have our value x0, this is our function is defined somewhere here, and, it looks like whatever, at g of x equals g of x0, we know that there exists a point c where the derivative of g at that point equals 0. So by Rolle's theorem, Rolle's theorem, bang, we know that there exists a point, we're going to call it c1, in between x and x0, such that the derivative of g at that point c1 equals 0. Boom. This is our first result. And now we're not finished quite yet, but the idea behind this is that we're going to repeat this now multiple times. So bam, g at the point c1 equals 0. Well, now we want to find what actually is the derivative of g of t. So let's try to find the derivative of g of t. And again, it's not going to be very hard. It's just going to be the derivative of f of t, because this is our variable, times the constant x minus x0 to the power of n plus 1. We just copy this over. And then again, minus, well, f of x is just a constant, so we just copy over the constant. And then, this term over here is the same as, let's say like x minus 1 to the power of 3. The derivative of that is just 3 goes over here, and you subtract this by 1, so this becomes a 2. It's just the classic, the classic power rule and chain rule. So this will be f of x times n plus 1, and then you copy down the constant t minus x0 times n. So we subtract 1. This will be the derivative of g at the point t. And now, what we kind of want to do the same thing again now, because we want to get to the n plus 1 derivative of g, because kind of that's in our final result. But now all of a sudden what we're going to figure out is that g of x is no longer 0, because again, if we plug x over here, if we plug x instead of t, we won't have such a nice thing as we had before, where the two terms were exactly the same and they canceled. Now there's n plus 1 here, so they're not the same anymore. But we still see that g of x0 equals 0. So first of all, I'm just going to write the derivative of g at x0. Well, that equals f at x0 times x minus x0 n plus 1 minus f of x times n plus 1 times x0 minus x0. Again, t becomes x0 to the power of n. Again, this, boom, this x0 minus x0, that goes to 0. And this over here, what we said, with our information of capital F, we know that f at the point x0 also equals 0, because, that's how the Taylor series is defined. That's how we define this remainder term. At x0, these two have to be the exact same. So this also equals 0. So again, we get the derivative of g at x0 equals 0. Bang. But we can't say the same for x, but we can say the same thing for c1. Again, by Rolle's theorem, we know that there exists a point c1 somewhere in between x and x0, such that g of c1 equals 0. And this is really clean. And now we can use Rolle's theorem again. And just to see, before we had our point, let's say x here, then we had our point x0 here. And now and we know that g equals 0 here and here. And now we know that there's a point c1 where the derivative of g equals 0, and the c1 is somewhere in between here, So we can just say that the point c1 was, let's say, over here, c1. And now all of a sudden we know that on this interval between c1 and x0, the derivative of g equals 0. So it equals 0 here and here. And again, this interval is contained in our original interval, x0. It'll be a smaller interval, but it will still be inside our bigger interval. So basically now we know that g at the point c1 equals the derivative of g at the point x0, and this equals 0. So now we can use Rolle's theorem again. Rolle's theorem. and we know that there exists a point C2 now somewhere between the interval C1 x0. So somewhere between this interval over here, we know that there exists a point C2 such that the second derivative of g at the point C2 equals 0. Again, so, we just imagine we can define a new function like, m of x, and that equals, the derivative of g of x. So, and then we can just say that, the derivative of m of x equals 0 again. Like, this is just, we just take the derivative again, basically. So now we get this nice result. And now the idea is we keep on repeating this, for the second derivative, we find what the second derivative of g actually is. What is the second derivative of g of t? Well, and that would just equal the second derivative of f of t. Copy down the constant x minus x0 n plus 1. And again, minus f of x. Here the n gets carried over once again. So we keep the n plus 1. We add the n. Then we get t minus x0 to the power of n minus 1, because, again, we subtract 1, the classic power rule. And then, again, we see that g, the second derivative of g at x0 will equals the second derivative of g at x0 will equal 0, because, again, when t is x0, this will be 0. Bang, this goes to 0. And we know that the second derivative of f at the point x0 is also 0. With the information we found out before, we know that at x0, every up to the n derivative, g at x0, the derivative equals 0. And again, we know that also this equals the second derivative of g at c2, and that also equals 0 by the previous Rolle's theorem. And then we can use Rolle's theorem again, and we can say there exists a point c3. And we keep on doing this. That's the whole beauty. We keep on doing this n plus 1 times. So we take n derivatives, but we apply Rolle's theorem n plus 1 times, because the first time we only applied Rolle's theorem without taking the derivative, and then each next time we took the derivative. So at the end, we're gonna get that g n plus 1, so the n plus 1 derivative of g at the point, well, I can call it c n plus 1, but in our proof over there, we called that point epsilon. So we know that g of epsilon equals 0, and this epsilon, the c n plus 1 point would just be somewhere between cn and x0. Again, if we look at our original thing over here, then somewhere here is the point c2, and then we're looking at this interval, and then somewhere here can be the point c3. So we're kind of getting closer and closer to x0. But basically, we can say that this point epsilon is between cn and x0, but what can we also say? Well, all of these intervals are contained in our original intervals. The easiest thing to say, because obviously we don't know where these points c1, c2, c3 are, we can say that this epsilon is somewhere in our interval x0. Again, in the original example, if x was 1, if we're looking at the error, of our approximation up to the second power at x equals 1, then, this epsilon would be somewhere between 0 and 1, because 0 is our point of expansion. If we expand it at the point, 1, and we're looking at the error at the point 2, it'll be between 1 and 2. So this is our big result. The n plus 1 derivative of g at a point epsilon equals 0 for an epsilon between x and x0. Now we are almost done with the proof. The only thing we still have to kind of do to finish it is find what actually is the derivative of g. What is the n plus 1 derivative of g? G of t. So again, I'm going to copy down g of t. I said that g of t equals f of t x minus x0 to the power of n plus 1 minus f of x times t minus x0 n plus 1. This is what g of t equals. And then again, if we keep on taking the derivatives, these are constant terms, so this is a constant, this is a constant. They're just going to get copied over. The only thing that's not a constant is, this over here and this over here. So first of all, let's, so we just have to find the derivative of these two things. So let's first take the dn plus 1th derivative of with respect to t of t minus x0 n plus 1. So, x0 is a constant, t's are variable. Well, as we saw, the n plus 1 keeps on being carried over. I mean, this power keeps on getting carried over. So, we're going to get n plus 1 times n minus 1, and then it will keep on getting subtracted here. So if we do this n, n plus 1 times, at the end we're going to subtract, n plus 1 from this. So this will be to the power of 0, which means that this whole term will just turn to 1, and we're going to be left with times 1. Basically, what we're going to be left with is n plus 1 factorial. So if you take the n plus 1 derivative of this term over here, what we're going to be left with is just n plus 1 factorial, which is really, really clean, and this t disappears, again, because t is just a random variable. We don't actually know, we don't know this variable. We kind of don't want it in our final answer. It's a dummy variable in between, and we can see that very cleanly, by making this to the power of n plus 1, t disappears, and we're just left with n plus 1 factorial. So this is really, really clean. And now, if we want to take the derivative of this one, the n plus 1 derivative of this, I'm just going to say it like this, n plus, because I'm not going to write n plus 1 dashes. We don't know how much n is. But this, well, we know that what does f of t actually equal? Well, we said that f of t equals, I'm going to write it here. We said that f of t equals our actual function, f of t, minus our Taylor expansion, tn, and then this is also, based on t, just instead of x. So the n plus 1 derivative of this, well, the derivative is a linear operator, so, it's the derivative is linear, so I can just distribute the derivative to each term. So it's the n plus 1 derivative of our function f minus the n plus 1 derivative of our function tn. And notice that this tn, this is the Taylor expansion up to the degree n. So if n equals 2, like it did in this example, we only took we expanded the Taylor term up to the power of 2. So this is a polynomial of degree 2, and we take the n plus 1th derivative. So this is 2, we take 3 derivatives. And if you take the n plus 1 derivative of an n degree polynomial, we know that always has to equal 0. This has to equal 0. Again, if we have a polynomial and its max power is x to the power of 3, and if we take n plus 1 derivatives, the first derivative will be 3x squared, then we're going to get 6x, then we're going to get 6, and then, the n plus 1 derivative, or the fourth derivative, is going to be 0, because it's just a constant. So the n plus 1 derivative will always be 0 of an n degree polynomial. So all we're left with is this. So the n plus 1 derivative of our capital function of t will just equal our normal function, n plus 1, the n plus 1 derivative of our normal function of t. So g of n plus 1 is n plus 1 derivative of t would just equal our normal function f n plus 1 derivative of t times the constant x minus x0 n plus 1 minus, again, our function f of x, which is just a constant, times n plus 1 factorial. This turns into n plus 1 factorial. And now we know that this function, g n plus 1, at the point epsilon equals 0. So if you put epsilon over here, g n plus 1, I'm writing this too sloppily, but g n plus 1 of epsilon will just equal f n plus 1 at this point epsilon. I'm calling, why am I calling it epsilon? I think this point is called psi, like the Greek letter for psi. I actually don't know. I'm just gonna call it psi. Times x minus x0 n plus 1 minus f of x times n plus 1 factorial, and we know that this equals 0. G n plus 1 derivative of g evaluated at this point equals 0. So now we can just rearrange our terms over here, because again, we're solving for f of x, and we see our variable t disappeared, which is really clean. It's an intermediate variable. It just helped us out, but now it's fully gone. And here it was replaced with epsilon. And if we want to isolate this, we put this on the other side, and then we divide by n plus 1 factorial, and what we're left with is just that f of x equals, I'm just copying this over, so f n plus 1 of epsilon times x minus x0 n plus 1, and then I divide by n plus 1 factorial, and this is exactly our answer that we were searching for. This is literally the remainder term, and again, f of x, or f of t, is equal to, f of x, which we defined it up here, bang, is just the same thing, or f of t is the same thing as Rn of x. We just use the dummy variable in between, but this just equals to Rn of x, and this is our remainder term. So our remainder term, if we're evaluating the function, if we're evaluating our Taylor function at the point x0, if we want to see what our remainder is at the point x, this will be our remainder. And again, this epsilon, this fn plus 1 derivative of epsilon, we know that this epsilon is somewhere between x and x0, and we can usually bound this, saying that it's less than or equal to m, and then this algebra becomes way easier. And this is how we get this term, or this is how we get Lagrange's remainder, or Taylor's remainder. Then you also have Cauchys remainder, which I think is expressed with an integral, something like that. But yeah, this is that. It's pretty clean. It's nice how everything works out. There's no complicated math. All you need is Rolle's theorem. So it's a pretty simple thing. But yeah, it's a pretty powerful tool, and it's used a lot when you want to actually know to how much you want to expand your function to, or just to get an estimate for your remainder. Because if you can't calculate the remainder as f of x minus tn of x, because maybe you don't know what f of x is explicitly. But yeah, that is it. Thank you for watching.